The electric field is defined as the negative gradient of the electric potential. Now, why would we bother defining this? Well, if you recall our force equation from before, we can actually come up with a nice clean formula of force equals QE. Notice, the electric field only depends on the potential gradient. This means that's defined at all points in space, even if you don't place a charge there. Once you put the charge there, you can calculate forces on that charge. In fact, we have two units for electric field. According to our gradient definition, we could say electric field is volts per meter. However, according to our force equation, we could say that it is newtons per coulomb. These are in fact identical, but make sure you understand why those units exist. Now, when we draw electric fields on contour maps, they use the exact same rules that we saw for our gradient. However, they now point in the opposite direction. However, we typically don't look at contour maps. Instead, we use field lines. And for field lines, we have 4 different rules to keep in mind. First, field lines for the electric field always start on positive charges and point toward negative charges. Second, the field lines always point in the same direction as the electric field. Third, the number of field lines is proportional to the amount of charge you have. Fourth, the closer the lines are, the stronger the field is at that point. So let's think about some contrasting cases of field lines. What if you have a positively charged plate just like this? Well, the electric field lines point out from it according to our rules. If I increase the number of lines, that means I have a bigger charge on this plate. But now let's compare that to a negative charge plate. All the lines will point into it, and depending on the amount of charge, I'll have more lines. But what if I bring those two plates together? Those electric field lines will superimpose, so that between the plates, it'll be doubled, but outside the plates, it'll actually be canceled.